with the recording. Let's see. Okay, we are recording now. So let's go to the slides, please. So the fourth step of this process is the analysis of the spatiotemporal distributional mobility. So inside the distribution in time, there is a kind of mobility. As I said, this is not the mobility that we can find in, transportation or migration. No, this is not this kind of mobility. It's the mobility inside the distribution, okay? So in this process, this is the second step. So after the exploratory analysis with the box plots or the scatter plots and Moran's high in order to look for regimes, spatial regimes, or with data kernels too, we go further. A new step will consist in the analysis of this distributional mobility with Markov chains. So now we are not taking into account the spatial dependence issues that this is what we will do the next day. The last day, we will tackle these 4 steps. These 4 steps are much shorter, so they are not going to be I will prepare, of course, the slides, but they are going to be a few slides compared to the other topics, the other lessons. And I will only ask you to understand the spatial Markov chains or the LISA methods, since I've already explained in the first session, so I will go on quickly to that, even the GIMA and the rank decomposition index. So there are different ways of dealing with a spatial dependence and with a spatial regime. So the 2 spatial effects that we take into account when doing spatial analysis, which are spatial autocorrelation and spatial heterogeneity. Okay, so now we stay in this classical Markov chain. So they are the standard Markov chains analysis. And so now we go to this Markov chains step. Oh, this is a mistake. So we are not here in the exploratory analysis, but in this second step of the Markov chains. And well, the first question is, why computing transition probability matrices? So if they are something that are, adding, if we are adding something new, something different. Oh, sorry, I don't know why. I cannot avoid this. So, sorry. This is what I want to answer here. Why computing transition probability matrices? So the density functions enable the characterization of the evolution of a global distribution. So this is the idea. We are analyzing a global distribution and the shape of this global distribution. So intending by global distribution, population, income per capita, or the emissions, the CO2 emissions, or whatever other phenomena. However, the density functions do not provide information about the movements of the spatial units within this distribution over the course of the study period. So they do not say whether the right tail, so this right tail this is the density function for population of the Chilean cities in 1930. And we have here the right tail. So we don't know if the cities that are in this right tail are the same cities that are in this right tail in 1952. So it's quite similar. The distributions are quite similar from 1930 to 1952, but it is not sure that the municipalities or the cities that are part of this right tail in the first period are going to be the same that are in the right tail in two decades after. Okay, So one way to answer these questions is to track the evolution of each spatial unit's relative value over time. So we can make a tracking. What happens with this city? Well, this city is I don't know, perhaps in the last quantile in the first year, but it jumps to the quantile, the fourth quantile in the other period, and so on and so forth. And we can do that in an automatic way, not tracking all the observations. That could be very tedious and very complicated to do. We can estimate what we call the transition probability matrices that are associated with Markov chains. This is why Markov chains are necessary, to know if these parts of the kernel, we can divide the kernel, discretize the kernel into quantiles. They could be quartiles, 4 parts, quintiles, 5 parts, sextiles, 6 parts, and so on and so forth. But yes, we must know, or should know, if the observations that are in one of these quantiles in 1 year are the same that the ones that are in this same quantile a year later or some years later. This is the point. This is why we introduce this new technique, because if not, someone could ask you, why introducing so many things? So we have here all the methodological procedure. This is what one referee asked us. Why doing such a messy thing? Why are you employing? So we tried, to explain in the paper the reason why we are using so many techniques. They are not, something like in a circus that I use many things just to enjoy or to make things happy, everybody happy there, smiling. No. I'm using that because all of these techniques are necessary if we want to understand the spatiotemporal dynamics of a phenomenon in time. So this is the main reason. The point is explaining why each of these techniques is different or adds something useful to the previous ones. And in a Markov chain, the probability of a random variable, we call this random variable x, which is equal to some value, the small x, at time n plus 1, given all the x values that came before it in the sequence, is equal to the probability of this x being equal to the small x at time n plus 1, given just the value of x that came before it. This is the main issue. So we are talking about an R1, so a time series or a regressive process of order 1. So only the previous time is determining, the value in the next period. So, in other words, x, this variable, population or whatever other variable, at time n plus 1, so in the next year, the next hour, the next month, the next decade, as it was the case with our population variable, because they were cities and we had the data only for decades because of the census. So x at time n plus 1 is only dependent on the value at time n, not any other value. This is very important because we are supposing that this happens, but maybe not. So when you are using models, you shouldn't forget, at least you must take into account the issue that theory is important here. So what happens really? We could say that our phenomenon, population of cities, really in the value in the next decade, really depends on the values of the size, the city size, in this previous moment of time? Or they have more memory, perhaps 2 periods, 3 periods? So this is not always easy. So in, econometric methods, we can apply Durbin-Watson or some other tests, to see. if we are in an R1 or perhaps R2, R3, or whatever other autoregressive orders. Okay, so in spite of that, you know that if we have a serial autocorrelation, it is going to be almost for sure of order 1 and perhaps of order 2 or 3. But if I have a spatial autocorrelation of order 2, it is because very probably, almost for sure, I have a spatial autocorrelation of order 1. So because it is the closest observation to the one I'm analyzing. This is why it is so important. And this is why many real-world situations can be modeled as an R1 or as a Markov chain. At any time, the only information about the chain is the current state and how the chain got there. At the next unit of time, the state is a random variable whose distribution depends only on the current state. So the state is the quantile or the quintile. So if city size or whatever other, per capita income, some other emissions, the emissions of CO2, whatever other phenomenon, okay? If they are in the lowest class, because they are very poor, they are very small, if I'm considering population, or they do not contaminate at all, almost, okay? Because if we take into account the CO2, if I am in the first class, it's low values, okay? So how it is, the way it is going to evolve in the future will depend on the situation now. This is what we are saying. It is very important because I've told you, I'm aware that I told you some days ago, please look for whatever panel database. Yes, but maybe the phenomenon that you are analyzing is not a proper R1. So perhaps Markov chains cannot be used, or you cannot use Markov chains for this specific database. This is something important to think about. Sometimes when you consider very short periods of time, you are not going to have an R1. It is more probably that you get higher orders because these periods of time are very short. If you consider decades, as me, with the population data, it is going to be almost for sure an R1 because the evolution of a city in 10 years, in the next decade, will probably be dependent only on the situation in this present decade, because I'm taking into account 10 years. That for a population, a city-sized population, it's and I think that could be a proper lag, a proper period of time. So it is something that you should think about. So, young people, I'm not so young, so this is why I can say that young people are used to apply the software, to press the buttons, or to run an R script very quickly, boom, and you boom, 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 set all the charts, beautiful charts, fantastic maps, whatever things. But what it is really complicated is thinking about that. And this is what makes you successful when writing papers. The way you interpret these fancy and lovely maps and charts. This is why I stop here, so much, looking for theoretical issues when I, go a step further. So I must think about these theoretical issues. I must think about the outcomes, why yes, why not, etc. So, well, the Markov models consists of a set of discrete, discrete states. These states, as I said, I'm going to eliminate. Okay. As I said, these states could be discrete states. Discrete states like, I don't know, different means of communication. So if people goes or takes one person takes the bicycle to go to work, or if he or she takes the bus or the car, so they are different modalities, different categories. Of course, you can apply Markov models to these kind of variables. They are perhaps the properest ones. But the thing is that we also can discretize, when the variables are continuous. What we do is discretize the continuous state space of this variable. The state space is the span, the variation of this variable. And this is why, well, this S, which is the state space of the variable, the states can be or must be split into R. Well, R can be whatever, the quantiles, the quartiles, so if it is a continuous variable. This is something important, because now perhaps you are wondering, and why quintiles? So the professor, so me, have used quintiles for the population. Oh, excuse me. But why? Why quintiles? This is something that you must decide. Maybe quintiles are not the best discretization. Yeah, it is quite common, yes. So if you ask me, but is there any discretization that is the most frequent, common, useful, whatever adjective you put there? Well, I don't know. Perhaps quartiles, 4 parts, quintiles, and 6 tiles. So 7 tiles maybe are too many, and only 3 divisions could be too low, but that's not a rule. So perhaps we should have some tests, and we really have, I will show you later. And because this is quite arbitrary. So we have, in spatial analysis, we have some arbitrary issues, like the spatial weight matrix, Well, this is one arbitrary issue. When I deal with a continuous variable, I must discretize this continuous evolution, and this is something that there's not a rule to do that. So something arbitrary in the end. So the Markov chain methods describe a process that starts in one period. I can consider even hours, years, decades, etc. So a process that starts in one period, in one of these states, one period, one class, and moves along the periods successively from one state to another, or not, you can stay there. So each move is generally called a step. So when, some observation, some city, region, person, whatever, moves from one state to another state, in the past, considering the future, so I say that he, she, or it has moved one step. If a region, or as I said, a spatial location, it can be a region, it can be a city, or whatever, is currently in a state Si, and it moves to a state Sj at the next step, it occurs with a probability denoted by Pij. So when you see in these papers that deals with Markov chains, Pij, what is Pij? Pij is a probability. A probability that a region or a spatial unit, whatever unit, is currently in a state, currently at present, in a state Si, and moves to another state, Sj, at the next step, so at the next period. And this is called the transition probability. So when we have all the transitions probability, we have the transition matrix, okay? And when a region remains in the same state, which is quite common and very frequent, in the same state that it was in initially, this occurs with probability PII. So PII is because it remains in I, okay, in this state I. The transition probabilities can be arranged in a square array called the transition matrix P, such that the values in a specific row, the first, for instance, represent the probabilities that a spatial unit or region in a specific state, in the present, will move to this first state. So the probability that the spatial unit in a specific state will move to this first state. So for instance, the cell 1,1, so it's a region that is in a state 1, move or remains in state 1. But if a region is in state 2, the cell 1, 2 is the probability in this cell, so 1, 2, is the probability that a spatial unit in 2 will move to first. So this is the way we should interpret this matrix, which is very important, you know. Now, in the next slide, this is what we represent here. This probability can be estimated. So this is the estimator. So the estimator is in fact primarily is a very complicated formula, but in the end it ends up to this very similar, very simple formula, in the sense that in the numerator we have the number of times a region started in a state I in period t and transitioned to a state j in the next period. So j can be the same as I in this case. So we have this matrix. This is the matrix of the movements or the transitions. So this 219 means for the Chilean cities that there are 219 times of or instances in which a town in the first quantile that I've given a name of a small town, that a small town at present remained in this same class of being a small town then in the next decade. So 219. Only 33 and 6 and 1 are the rest of the instances to sum the 259 that are more or less the number of instances for each of the quintiles. So what I've done is given a name to the quintiles as if we were considering really discrete classes. So I could consider the first quintile of population as a small town, and the second quintile we could call these locations as towns. In the third quintile we have cities. In the fourth quintile we have the big cities, and in the fifth quintile we have the megalopolis. You know, so well, it's a way of giving a name and to to make interpretations easier. It is not always possible to give a name, but why not? It is could be valid to do that. So in this case, this 33 means the probability. Oh, sorry. As we said here, a probability that a spatial unit, a city of a region in a specific state, in this case being in town, will move to this first state. So here, these are the probabilities, and here we have the instances. So with respect to 259, 219 is an 84%, more or less 85%. So, and this is what this probability is taking into account, you know. So with respect to the total jumps or the total possibilities in one moment of time of jumping to a small town, jumping down in this case, or staying in the same class, so the number of instances are 259. That is the number that goes to the denominator of the probability. And in the numerator, we have the number of instances that, in this case, a state, so starting as a small town, in the next decade, wherever the decades end up in a small town. Here, the number of cities or enclaves or whatever locations that being a town, so staying in the second quintile, end up in one period, end up in the next period in a small town are 33, and so on and so forth. So this is how we should interpret these results. So it's 12%, almost 13%. If starting a city and jumping down to a small town only happens in 2%, and it's almost zero and totally zero, the probability than a big city or megalopolis, of course, in one decade jumps down to being a small town in the next decade, as is usual, because 10 years cannot be enough. Perhaps in a war or something like that, that many people migrate or even die or whatever. So it is very complicated to jump from being a big city in one decade to be only a small town in the next decade. But this is what this matrix is saying. So as you can see, and we saw in other examples, so in the main diagonal, we have this PII. So the probability that starting in one class at present end up in the same class in the next period of time. And this is what predominates, particularly in the first and last classes, because since it is a continuous variable, the first and the last corresponds to the observations, the spatial units, with less and more values. So the lowest and the highest values. In the case of cities, well, it's very complicated. If you are a small town, to escape and grow sufficiently as to jump up. No, so this is what this is how we should interpret this result, and the same with the megalopolis. So the only possibility for if you start being a megalopolis, well, perhaps you can end up being a big city with 7% probability, but the rest, so 93%, corresponds to the same class, because most frequently megalopolis is not going to lose so many population as to jump down to the other class, to the class that is just before. And this is how we should interpret these results. So it's normal. We have here the number of instances. So it's 2. So being a megalopolis, so only in 18 instances, a megalopolis in one period jumped down to being a big city in the next period. This is the 241 rest of the instances, they remained being a big city. So it is logical that we find the lowest or the lower values for the main diagonal in the intermediate classes, because in the intermediate classes there could be more easily find these jumps going up and down. If for instance here there is the possibility if a city starts being a city well, with a 70% probability, in the next step it will be going on being a city, but I have 17% of possibility that this city converts into a town because can lose population or even grow. It gets population with 10% probability. In the next step, it could be a big city. So it goes from city to big city. Okay. Something that is important, as I said before, is the evaluation of the Markov property. So in Bickenbach and Bod, this is an old paper from 2003. It is a very interesting paper because they develop some tests in order to see if the discretization, when, for instance, applying this discretization to income, because at that time, during the first years of this century, there were a lot of papers. If you remember, Julie Legallot wrote a paper in 2004, and they were devoted to analyze GDP per capita. Previously, in QA applied to the countries, to the world countries, and afterwards, since the 2001 paper written by Serge Ray, that was applied to the United States regions, it became to be applied to the European regions and some other places regions. And so this is why, well, it was applied to study economic convergence, but it can be applied to some other phenomena that is continuous, like population. So I can also analyze if I have a kind of convergence trend in population, or if you are analyzing the emissions of CO2, if we have convergence. So perhaps like 20 years ago, you will find huge differences among countries or among even regions, I don't know, mostly among countries, in terms of CO2 emissions. And now the world countries have reached to a convergence point because everybody has made an effort to reduce the emissions, or not. This is something that you should conclude or analyze, the ones that are or wants to analyze this topic. Okay. Something that Bickenbach and Bod says is that the estimator is consistent, but this is something very important, asymptotically normally distributed. Why asymptotically? Because the estimation method, so this PIJ probability, this estimator supposes or is based upon the assumption that we have enough sample, so a sample that is enough to represent the population or to represent the data generating process. That is the theoretical phenomenon you want to interpret. You are taking a sample. In fact, for Chile, we took, some cities that are considered cities in the statistics office, and we considered this sample because we considered it as representative of this data generating process for the urban system in Chile, which is very theoretical. Urban system, contamination. They are big words, very big words. But you are extracting a sample. Of course, you do that trying to do your best, to take enough data, etc. But this is something that we should test, maybe. And if our sample is too small, perhaps we cannot rely a lot in this estimator. So this is what Bickenbach and Bod stated in 2003. They said that improper discretization of a continuous variable, like per capita GDP, etc., could have an undesired effect on removing the Markov property. So this Markov property is the property of being an R1, so an autoregressive serial process of order 1. And we can lead or end up in misleading results. Yes, we will have results. We almost always have results, unless if you are working with geoda and geoda can explode and put you away. But you are going to have these outcomes. But the question is, are they reliable or not? Ah, the laptop gave me this outcome. Yes, the laptop, of course. But can you interpret it validly? Is it worth or not? This is something that corresponds to you guys that are studying the master course, because you want to be analysts. So you must think about what you are doing, not only relying on laptops. Yes, of course, they are going to do it very quickly and sometimes very well, but be careful. Eh? So why we can have this kind of misleading results, or we can maybe fail in getting this Markov property, because we have this degree of arbitrariness, as I said. So the cuts for the classes in these continuous variables are arbitrary, unless you have categories, proper categories, as I said. So taking the bus, so categories that are independent of one another, and sometimes they don't follow any kind of order. So one class is not higher or better than the other, so they are independent. But in this case, when we apply to this kind of economic issues like population, per capita GDP, GO2, that they are continuous, we can get this problem. Discretization methods must satisfy three conditions. Well, they say that too, but I have added a new one. So three. First, the classes should include a similar number of observations. So these observations are the instances. If you remember here, so we have that the sum of the instances for the quintiles are almost the same, with the exception of the third one, that instead of 259, we have 252. But we tried to satisfy this condition, as you can see. Second, so this is something that we should take into account. This second thing is not so easy. The data generating process, so the theoretical phenomenon from which the sample is drawn, from which I extracted this data, must meet the restrictions imposed by the underlying Markov chain theory. So this underlying Markov chain theory says that this sample, and at least the jumps of the steps from one period to another, is an R1. Otherwise, if it is not, the PIJ will not be good estimators and cannot be used to derive a limiting distribution. So this limiting distribution, or the ergodic distribution, is the long-run distribution. This is one of the many reasons we want to compute Markov chains, to see what is going to happen in the long-run future. So where we are going, which is our future, which is the future of urban systems in Chile, or the future for the emissions in Europe, or in the world. Okay? Or if we are going to converge in terms of GDP per capita or income per capita in Europe, for instance, which is one of the main objectives, or even in Spain, or whichever other country, in France. Okay? So we want to derive the limiting distribution. And please, if this Markov chain theory, this R1 assumption, do not hold, we are going to get the ergodic distribution, but maybe it is going to be no use or useless. Third, the PIJ have to be based on a number of observations, N and I, that is sufficiently large to be able to rely on the asymptotic properties of the estimators. As I said, this PI hat is an estimation that comes from a model and comes from some assumptions. And the assumption is that the estimator is asymptotically normally distributed. So asymptotically. Why? Because we are supposed to have enough data, enough number of observations, that the sample is going to be sufficiently large. Otherwise, the accuracy of the estimates will be rather poor. They are not going to be accurate. And the same, we won't be able to rely a lot on these PIJ hat values, okay? In practice, estimation is subject to a trade-off. So we have a trade-off. A trade-off between what? Between improving the accuracy of the estimates, okay, and increasing the probability of violating the underlying assumptions. So we must choose. So if we want to improve to the maximum the accuracy of the estimates of the PIJ hats, okay, we perhaps we will increase the probability of violating the underlying assumptions. Why? Because if improving the accuracy of the estimates is sometimes because I produce more data. How I can produce this data? Can I produce this? Sometimes splitting in more classes, so a smaller, instead of quintiles, 6 tiles, 7 tiles, 8 tiles, or whatever. So this is a way. But if I do that, the amount of time, if you can do that, is going to be very small, and you will probably will have not only an R1 but an R2, R3, which could be significant, and I will violate these underlying assumptions of the Markov chains. I don't know if I explain myself correctly. So in principle, it will be preferable to estimate the probabilities using as many observations. So this is in principle, using as many observations, transition periods, or spatial units as possible. Yes, this is in principle. However, the shorter the time intervals assumed to constitute one transition period, the time intervals, the higher the probability of violating the Markov property of time dependence. This is what we say here first. But the longer the time period under consideration, no, instead of 1 decade, 2 decades, okay? Instead of 1 hour, 24 hours, right? But the longer the time period, the higher the risk of structural breaks or time heterogeneity. So it's not easy to see what to do. And well, this happens also with the spatial dimension. In the spatial dimension, the smaller the spatial units, if you can choose. Instead of cities, I don't know, districts or something smaller, the higher the correlation between variable levels of neighboring regions, so the higher the spatial dependence. If I use census tracts instead of neighborhoods, like one of you is doing or trying to do, one of the persons that are listening to me now, you are going to have higher spatial autocorrelation when you go down in the spatial scale. But the larger the geographical scope, well, I will aggregate, not neighborhoods, even districts or municipalities, the higher the probability of lumping together regions with a heterogeneous development pattern. So I will sum up and make compute sums or averages that do not correspond to the this very important thing we have here, the data generating process. This data generating process, it's a headache, because we should think about it. How is it exactly, and how approximating it as good as possible, taking into account all these limitations and all these problems that we could have. Sometimes you said, well, I am using countries because I don't have regions. Okay, Or I'm using sensor structs. Well, with sensor structs, you can add up and sum or computing averages in order to get higher or larger spatial units. But sometimes this is the contrary. I cannot use sensor structs because I don't have the information at this level. Yes, sometimes you have limitations in the data provision. But you must be aware, at least you must do something that not many people do. Think. Think about the data generating process. Think if you are really representing it properly, if you have data limitations, what conclusions or what consequences these limitations are going or could have, etc. Okay. So Bickenbach and Bode present two tests for time homogeneity or stationarity. These two tests are present in SDAR, and it is interesting to analyze this time homogeneity. This is the likelihood ratio. The LR is likelihood ratio, and the Pearson's chi-square test. There are two statistics that are quite similar, and the outcomes are more or less the same. These tests are appropriate for deciding whether the transition probabilities of the first order Markov chain can be assumed constant over time. So if these transition probabilities holds for the whole period. So we think, for instance, for Chile, that we have a structural change in 1970. I don't know if you remember that we had different for the in the other slides for the mean averages. We found that 1970, with the change in the economic policy, with a change even in the political regime, with a dictatorship, things changed a lot, even in the urban system, and we had a different structural change, so a different structure. And if it happens, this is what this test is evaluating. To what extent we have a structural change in the middle of the time span. So in our case, this time span comes from 1930 to 2002, if you remember. So what this test is testing, is contrasting, is to what extent this PI that I have computed here for the whole time span holds, or if they change. I can consider splitting the sample, but I'm going to have much less observations here. We didn't, because it was a mess doing that in the paper. So in the paper, we considered as if we didn't have this structural change, okay? But why? Because if we consider the structural change and altogether the spatial regimes, perhaps the number of instances were going to be too low. And we wouldn't rely on, because these asymptotic assumptions are not going to hold, and we couldn't rely in the accuracy of these PIJs. So we want to be so explicit, so detailed, that I'm losing this structure that is supposed, I'm losing the properties that I'm supposing in the Markov chains theoretical issues. But we had this test available. What this test, both tests does, is dividing the entire sample period in T transitions into M. So M is, the complete set of transitions, our 8 decades in the Chilean case, in the example. And what we do is considering subsamples of these periods. So from 1930 to 1970, and from 1970 to 2002. So we split the complete time span into 2 subperiods. This is what the test does. So you should tell the test how many subperiods you want to consider. And what the tests both tests do, is comparing the transition matrices estimated for each of the m subsamples. So like a Chow test. In the Chow test, you have a kind of F test that considers the errors estimating the model for the whole time span, or subdividing the time span into 2 subperiods and estimating 2 different models for the subperiods. So of course, the errors are going to be lower for the subperiods, but what the F tests say is if it works, subdividing and losing degree of freedom in the model, or considering the whole time span. This is something similar to what these tests, both tests are doing. And of course here the null hypothesis is homogeneity. So homogeneity is that it doesn't work subdividing into 2 or 3 or more subperiods the whole time span. And well, in the test, additionally, to obtain estimates of comparable quality, what they do is subdividing the m periods in such a way that they have about the same length. So if I say subdivide in 3 subperiods, what it is going to do is dividing the 8 decades I have in my database, 8 decades, into 3, more or less these 3 parts of the same length, same amount of decades inside. Okay. Well, in our paper, well, the first condition, if you remember, that was the first condition was that classes should include a similar number of observations or instances. We find that we have this more or less same number of observations as we said. Second, we apply this discretization, so 5 classes and 2 subperiods. This is what we tested, and because we think, or this is something that we was testing, if they perform best in the first order test for the Markovian property. This is what we supposed. Then considering any other kind of discretization methods, for instance, quartiles instead of quintiles or sextiles, or even natural breaks, or some other kind of divisions of the distribution. And not only the division in classes, but also different kind of different times of subperiods, not only 2, but perhaps 3. Because in 1950 we had another important change in economic terms in Chile. So we could consider from 1930 to 1952, from 1952 to 1970, etc. Okay. For the group of Chilean cities, the test values corresponding to the quintile discretization periods were, this number, 35.76, the p-value allows rejecting with 96% confidence. And, well, in this case, it is not so clear. The likelihood ratio allows rejecting with 90% confidence, but it is not so high. So in this case, perhaps we have some doubts of this structural change in the middle is not so significant. Okay, this is our conclusion. And well, for the moment, unless you ask me for something, you know, well, the ergodic distribution is the last chapter, yes, and this is for the moment the contents for this step or this part devoted to Markov chains. If you in the feedback assignment ask me to explain something better, so I will add up more contents to these slides. And well, regarding the ergodic distribution, sometimes is the main objective for Markov chains. This ergodic distribution is the distribution the limit distribution or the steady state distribution that can be interpreted as this long-run equilibrium situation. So it's the situation when all the cities will stuck and do not move anymore, do not grow, do not lose population. So they will stuck there. This is the long-run equilibrium. This function is used many times to assess the form of convergence in terms of income, population, or even in other terms like contamination or whatever. A concentration of the frequencies, well, I've explained in other parts of, in other slides, but I will repeat. If the frequencies of the ergodic distributions are concentrated in a certain state, for instance, in the mean state, so the average, so we could conclude that in this set of spatial units for this phenomenon, we will get in the future convergence to a mean value. So they are going to converge, and the small ones will be more or less an average size, and the megalopolis also will lose population to be a middle-sized cities. You know, this is the idea of convergence to the mean, to a mean value of whatever phenomenon you are considering. Concentrations of the frequencies in some of the classes, so a kind of multimodal limit distribution. So they could be interpreted as convergence clubs. So yes, they will converge, but to certain clubs of sizes. Maybe we will have in future a group of very big cities, perhaps not megalopolis, but very big cities, and another group that perhaps they are not going to be very small towns, but just towns. So, and these are the situation that is expected for the future, for instance, in Chile, for the urban system, or for whatever place. And finally, if we have a dispersion, we don't get very different values of probability values among all classes. This could be interpreted as divergence. So divergence is that they are not going to stop in a specific point. So the big ones are going to grow, and the small ones are continuing losing population. They are not going to converge. Yeah, okay. And so let's go now. Something that I would like to say. I have refined the slides. Go to Microsoft Teams. Here in the files in the files menu, in the previous session, I've refined the slides. So chapter 3, version 4, I introduced some references and changed or refined something. So please download this last version that you also have in Moodle. So in Moodle you can find this version 4. Okay. And now for today, if you want to download here in this chapter 4 the R files, you will find two R files. So one for the kernels and the other ones for the Markov chains. Okay, and we can just take a look. Well, I suppose that most of you know how R works. In spite of that, I have explained as much as possible what all the commands are doing. Okay, here if I press in this part, I can see the menu for this first file. consists of installing and loading packages, reading and managing the database, defining spatial regimes, defining well, the kernel density functions. And for these kernel density functions, what we are going to do is considering the full sample of the Chilean cities, splitting and considering only the central part of the country, so the cities that are part of the central regime, the northern regime, and the southern regime. So you can reproduce what it is done here with your own database. I've copied everything in a working directory. It's a very simple one, R class. So R class is it's a working directory that is depends directly from my Dropbox or my hard disk, because I have everything in Dropbox. But if you had it in C, in a hard disk, main hard disk, or some other hard disks, you should say first, just because I have included in this folder, the R class folder, well, both files and the databases. Well, first I'm going to work with Chile map 2. So Chile map 2, well, I don't know if it was the map we had, but Chile map 2, if I open this map, I think that this is the map we built when dealing with it in Geoda. But I will show the map, well, at least the table for this map. So I have the names. So in this map, it's a shape file. I have some fields that are not useful for the kernels or for the Markov chains. So this is why I should take this map and eliminate, or only considering these columns that are useful for us. So these ones that are the codes, if you remember, are not very useful. So, and there are some others that are not useful for R, because it's going to be, so these ones that were the population in logs and some others are not going to be useful. So the only ones that we will use are the ones with the P, that are for the population. So these P30, P40, etc. And well, so if I come here and set the working directory and press run, well, I recommend you to install these packages. So the RGDAL package is the package that allows us to read vector maps. I have silenced these ones because I'm not going to use them, but you could, of course, if you want to, for instance, read post-GIS maps, you will need this SF package, or to read TXT databases, perhaps with the packages in the base software, it's enough. Or if you want to read Excel files directly, you should install OpenXLSX package. For me, the only one I need is RGDAL, because I have my database inside the map, and this is why I load this package, because I've already installed it. Additionally, I will need the ggplot2, because in order to depict, or to represent the kernels, I will use this package. So I run again this package that was already installed. So what I do here is reading the map. If I read the map, it says that it has 184 features. They are the cities, and 33 fields, and it is called Chile map 2. Okay, what I do is giving a name to the years. So I create this vector with the year names, and I will transform this Chile map first as a double entry table with as data frame. Okay, now what I get with this B is a data frame that has this form. I can also look at it. I have all the variables that were complicated to open in Excel, and now we could open very, very easily. And now what I'm doing is selecting from 10 to 17 only the population variables, because as you saw, I had lots of columns that are useless for our study. And now if I open B again, I only get these population variables that are the ones that I need. Now I must transform the database into a numeric matrix. Why? Because it is necessary for the packages. And so I transform B now in a numeric matrix. So it seems as if it was the same, but it is not the same, because here it says num from numeric. And excuse me, sorry. And here the call the call names is the way we are going to name the. So I'm going to put a name to the columns with year. So the spatial regimes definition consider, well, first what I do is creating a new vector, which is a character, and that it's only the value is south, south, south. And I'm going to override the ones considering this field 2. The field 2 is now going to be necessary, and it is present in Chile. The field 2 has the regions in Chile. So the regions are named in Roman numbers, with the exception of the metropolitan region. And so I'm going to, as you could see, identify the rows that belong to this regime. And the same with the southern, well, sorry, this is the south. The south was already written. This first one was the north, and this other one for the metropolitan region, so the central area in Chile. So now for the kernel density functions, I need to set the seed to get replicable results, always the same ones. This is the reason why we want to have reproducible simulations, and to replicate the same results. We create now this function called den that is going to be useful now for what? Well, first, for the full sample of Chilean cities, what I do is creating this D that corresponds to the whole sample, and applying coerce the columns of B into the values of the density. Well, if I press everything, I compute the density values, for the decades I'm going to consider. So they are the ones that could be, these cutting points for structural changes, as you remember. So from 30 to 52, from 52 to 70 to 02. Okay, so I run, get the data, and now with the data frame, I combine the vectors for population, density, and year in order to create the maps. Well, these 3A are the figures in our paper. If you want to compare, we get here the figures. So you can export, for instance, this. You can export this figure. Pressing in export, you can copy to clipboard. Okay, copy plot and paste. Oh, okay, paste here. Okay. I suppose that you know how to deal with her, but if not, this is the way of copying a chart here. And you can do the same with the central spatial regime. You will be surprised because this regime is more or less the same, because you will find a lot of observations in this regime. And this is quite similar to the kernels for the whole country. This is the kernels for the whole country. These are the kernels for the central regime. And the northern and the southern were completely different, as you will remember, because I showed you in the slides. We find here these two modes, if you remember, from this situation of very similar modes going to a certain convergence to an average, but keeping this small mode. And the southern spatial regime that were also different from the central and even the northern. So in the beginning, we hadn't this two mode, only one mode, but it evolves to two modes. Well, a central one, which is more or less the same as the northern part. So if I compare the northern, so the end part is similar in the northern regime to the southern one. Perhaps the difference is, well, more or less in the value. Here, this second mode is not so large in size than this other second mode that are more in 125% over the average. And this is the way we compute these kernels. So perhaps for you it's not complicated, because some of you have in this first assignment, even if it weren't necessary, you presented me the kernels, so I know that you know how to prepare them. But what about the Markov chains? So the Markov chains, maybe since it is a little bit late, we can keep it for next day. The last day we will have 2 hours to finish, but you can run it all together, in the sense that if you have a clear console, okay? If you have installed previously, well, you have to install the star in some other packages. You will be able to run everything. So again, reading the data and computing the regimes, and now getting the Markov chains for the whole city or the whole country, and you can compute these Markov chains considering different spatial regimes. For the northern one, the southern, so the outcome, the output is the transition matrix, so the matrix with the movement, so the instances. This was the one that I represented on the slides, and these are the ones for it's the probability transition data. For the northern regime and the central regime, the northern one, you will see some differences, and well, I have represented all together in order to make comparisons. Here we have the steady state. So this is the steady state for the whole country, for the central part of the country, for the northern and the southern, and they are quite similar, but not exactly the same. So, for instance, in the northern part of the country, we have 3 higher values and 2 smaller ones. So they are probabilities. So the probability of getting towns of middle size, of also grouping some towns, very small ones, and grouping in megalopolis. So this is the future for the northern part of Chile, for the urban system in the north of Chile. And what happens in the, sorry, this is, yes, this is for the northern part of Chile, and what about the southern? So the southern, well, in the southern we have two clubs, or very small ones or megalopolis. And well, the central and the rest of the country, they have a similar figure, and what we have is divergence. So because, well, divergence because I have 0.20, 0.19, 2020. Maybe you could consider also these other values like divergence, since there are not a lot of differences among them. But of course, compared to the northern and the southern regimes, the central and the whole picture thing points to a divergent trend in future. Okay. And what about a graphical representation? So it is interesting because we can get a graphical representation. I recommend you to open as much as possible these windows in order to get better charts. So it's a way of representing the Markov chains. Okay, so there are not a lot of differences if you consider the whole country or if you consider the central regime, but you could have more differences considering the subsamples. This is the southern part of the country, this is the northern, this is the central, and this is the whole system. Okay, so I would ask you to, for the next day that will be on Wednesday the 26th, I think. Let's go here. On Wednesday, the 24th, sorry, the 24th, we have the last class. For this class, I ask you to, to compute until 2.5. So if you want, you can do the forecasting thing, but I will explain it the next day. It's not very complicated. So you forecast more than one step. This is the idea. But just to stay here, you should reproduce the kernels, so the first file here, and this second one until 2.5 point. So this is the index. So 2.5, the graphical representation, but not the forecasting states, because you can run the forecasting states, but I want to explain them, how to interpret them. Okay, and that's it. So we will see you on Wednesday the 24th. Okay, and please upload your assignments and correct the ones that weren't right, and please improve these presentations. Okay.
Professor?
Yes.
May I please ask a question? Well, for the previous assignment,
Yes.
Since we have so many years and the time player, so do we have to represent each of the year in our presentation?
Well, this is what I was saying. At first, I didn't say a word about, restricting this time span. Maybe what you should think is to what extent you will have a Markov chain of other one with your jumps from, with your steps from one period to the other period. Maybe you have hours, or you have weeks, or you have days, or even years. Maybe you could consider lustrums from 5 to 5 years, or decades, and you will have less number of periods, and perhaps you will get more easily the R1 Markovian property.
Okay. Also, I don't know, while trying to do my own assignment, the last one, I noticed that my local moran, the representation did not change over time.
Yeah, maybe it is because you don't have any kind of convergence, so things are going to stay the same. This could
Okay.
be the outcome, so the interpretation. Because when you get that the Moran psi value is higher, so it is a sign of going to convergence clubs or to divergence. And if it goes lower, so you will go to convergence. So you must consider that perhaps you are not going to have any movement. Perhaps
Okay.
because you haven't considered this time span is not correct. Try grouping the time periods. In
Yes,
last,
I did that.
oh, okay.
Then also my B slope was 0. I hope there's no problem with that too.
Well, I would ask you to do, please, because during this week I didn't receive from you any emails. Well, just only one or two. Please, all
Okay.
these doubts you should write down and ask me by email, because I could, give an answer directly to you, and because they could be, you could have different kind of doubts that your colleagues. Even I could upload your questions. And you could even open by yourselves. It is possible. You can open here a forum for discussion, and you can add, oh, excuse me, it is in Spanish or in English. You can add a new discussion topic, a thread. You can add your question, and I will answer, and maybe we can open a discussion, because some of you could have, or not, I don't know, the same doubts. Okay?
Okay, thank you very much, ma'am.
So see you on Wednesday. Bye-bye.
Bye. Bye bye.
Bye.
Thank you, Professor.